Hi, I'm Ali Sealander with UTD GeoNews, and today we're going to talk about what caused a large earthquake that recently shook Greece and Turkey. On October 30th, 2020, a magnitude 7.0 earthquake struck Samos Island, Greece, just off the shore of Turkey. This devastating quake caused over 1,000 injuries and unfortunately has so far resulted in at least 115 deaths, marking it as the deadliest earthquake of 2020. A resulting tsunami reached many coastal cities, including the beautiful city of Izmir, which unfortunately was especially hard hit, with over 20 buildings destroyed. This region is very seismically active. Over the last 70 years, it has seen 36 earthquakes with a magnitude of 6.5 or greater. The earthquake occurred 21 kilometers beneath the surface and was caused by rupture and movement on a normal fault. This is a type of fault where the rock above the fault plane moves downward relative to the rock below it. The fault movement is caused by extension or stretching of the rocks to the point of producing motion along the fault and an earthquake. The fault associated with this earthquake trends east-west, which means that extension is happening in a north-south orientation. But what is causing this extension, and why do we have all this faulting and seismicity in the area? To get to the bottom of this, we need to delve into the plate tectonics of this region. The Samos earthquake occurred within the Anatolian microplate, which is crammed between three other plates. To the north is the massive Eurasian plate, to the southeast is the Arabian plate, and to the south is the African plate. The Arabian plate is colliding with Anatolia, squeezing it against the Eurasian plate, so that Turkey has to escape to the west. Meanwhile, the African plate moves northward and sinks beneath a convergent plate margin. Here, the African plate subducts, or sinks, beneath the southwestern Anatolian microplate in a subduction zone. As a result of continental collision in the east and subduction in the west, the Anatolian microplate is very dynamic. This tectonic activity can be visualized using GPS, tracking how different parts of the Anatolian plate move in response to these different forces. What we can see is that the Anatolian plate is essentially making a plate tectonic U-turn. In eastern Turkey, the Anatolian microplate is moving slowly west-northwest away from the colliding Arabian plate. In central Turkey, it moves more rapidly westward. And in the west, the Anatolian plate beneath the Aegean Sea is moving very rapidly south. These movements are accompanied by a lot of deformation and faulting, which cause a lot of earthquakes all over the Anatolian plate. It was one of these faults, right in the center of the Anatolian plate, that slipped and caused this devastating timbalur. That explains the faults, but what about the stretching that caused the faults to rupture? The answer is found in the convergent plate boundary, about 350 miles south of where the earthquake occurred. The northern part of the African plate that is subducting beneath the Aegean Sea is very dense. In fact, it's so dense that as it is subducting, it basically falls back on itself. The subducting crust collapses and rolls backward to the south as it sinks. And even though the African plate moves slowly northwards towards Eurasia, the sinking and rollback of its dense crust is faster than the plate's movement, causing the subduction zone to retreat southward. Basically, for every one step forward, the African plate in this region is taking 2 steps back. And like a friend falling into a pool, the African plate pulls the Anatolian plate with it, stretching it along the way. It's this pulling to the south that is causing the stretching or extension several hundred miles north of the convergent plate boundary. As you can see, the Anatolian microplate is very active, and more earthquakes can be expected in and around the area in the future. Thanks for watching, and don't forget to subscribe to catch more episodes of GeoNews. See you next time!